So please.
All right, thank you. Thank you very much. Thanks for the invitation, and thank you everyone for coming. I will be talking about the pathwidth theorem for induced subgraphs, which is a theorem we proved recently with Sophie Spirkl, who was my PhD supervisor at Waterloo, and Chudnovsky, who was Sophie's PhD supervisor at Princeton, but she's also one of my mentors. So, and this is also part of an ongoing project that we have been working on for a couple of years. And we here mostly means Maria, Sophie, and myself, and sometimes others. So let me give you some context on that. So you see, if you like structural graph theory, which by and large means you like Paul Seymour's way of thinking about graphs, then you gotta agree the whole subject stands on two main pillars. It's induced subgraphs and graph minors. And I would like to think about minors as the heart, it's beautiful, almost poetic. And induced subgraphs to me is like the brain, it's like the intellect. It's technical, sometimes ugly, to be honest, but it's also very precise. So what we have been trying to do is, as far as I'm aware, among the very first attempts to get the heart and the brain to speak to each other. So, in induced subgraphs, we're almost always trying to understand how the global complexity of a graph manifests itself in its induced subgraphs that somehow share the same complexity gene, but they are far more structured than the host graph. And somehow the idea here is to ask the same question, except the measure of complexity is coming from, or at least has its roots in, the territory of graph minors. And specifically today I'm going to talk about pathwidth as the measure of complexity. And the good news is that we now completely understand what induced subgraphs you should expect to see in a graph of large pathwidth. Okay, so that's enough background. Let's get to the actual math. So I first need to tell you what pathwidth is. So let's start with this easy observation that if you just pick a path and a bunch of subpaths of the path, and you know that they're all pairwise intersecting, then some vertex of the path must belong to all of them. This is what you would call the Helly property of subpaths or something. And the kind of natural question you can ask here is, what if only some pairs of subpaths are intersecting and some are not? Then can you do any better? And if you think about it for a moment, you have this set of objects, the subpaths, and you're declaring some of them to be in a relation. In this case, it's sharing a vertex. And that's just another graph. So the pathwidth of that graph is the best you can do. This is how pathwidth ends up being a graph parameter. So here's the formal definition. The pathwidth of a graph G is the smallest positive integer, non-negative integer, for which you can find, so let's call it W, for which you can find a path P and a subpath of P associated with each vertex of your graph G, such that whenever you have two edges in the graph, the corresponding subpaths intersect. And every vertex of the underlying path is going to fall in at most W plus 1 of the subpaths. And here's a picture of a graph of, let's see if this works. Yeah, here is a picture of a graph on 7 vertices, which actually has pathwidth 1. Why? Because here is a path P and a subpath of P associated to each vertex of G, such that whenever you have an edge in G, the corresponding subpaths intersect, but every vertex of P belongs to exactly 2 of the subpaths. So 2 is 1 plus 1, that's what gives you the pathwidth to be 1. Okay? And I'm not going to be talking about tree width as much, but if you just take this whole thing and replace each word path with the word tree, you exactly get the definition of tree. And it comes from the same background. You have also the Helly properties of subtrees of the tree and so on and so forth. Okay. I will also be talking a lot about containment relations on graphs. Okay, as everyone knows, there are 3 elementary operations you can perform on a graph to make it smaller. You can remove vertices, you can remove edges, and you can also contract edges. The first 2 are quite clear, and the third one, at least visually, is what you think it is. You just fuse the 2 ends of the edge into one vertex. And here's the picture. So you have the 4-vertex cycle as your graph G, and if I remove the vertex y, I get a 2-edge path. If I remove the edge xy, I get a 3-edge path. And if I contract the edge xy, I get a triangle. So these operations are really different. And different combinations of these operations give you relations on graphs. So you have minors and subgraphs. Minors allow for all 3 operations. Subgraphs only allow for removing vertices and edges. And each one of these containments has an induced version. So induced subgraph means you only remove vertices, and induced minor means you only remove vertices or contract edges. So the induced version of a containment relation is really it's just the same, it only disallows removing edges. So this whole idea of an induced containment is very much about keeping an accurate record of adjacency. Whenever I'm keeping 2 vertices that are adjacent, I must keep the edge between them. And pathwidth and treewidth are monotone undertaking minors, which means they're monotone undertaking the other 3 containments because taking a minor is the weakest one. Right. So I assume most people here know all of these things, but feel free to interrupt and ask questions if anything is unclear. All right. So, like I said at the beginning, we would like to understand what causes a graph to have large pathwidth. So let's see a few examples. Complete graphs and complete bipartite graphs have large pathwidth. And that's boring. I mean, of course they do because they're dense, really dense. Well, there are sparse examples too. Subdivided binary trees and their line graphs, they also have arbitrarily large pathwidth. The pathwidth of a binary tree is, I don't know, half the radius rounded up, and subdividing edges doesn't decrease the pathwidth. And the same also is true for the line graph. But truth is, you really do not need to think about all 4 of these. Why? Because they all contain subdivided binary trees, arbitrarily large subdivided binary trees, as subgraphs. And this points us towards the amazing theorem that Robertson and Seymour proved in the opening paper from the graph minor series, that any graph of sufficiently large pathwidth contains a subdivision of your favorite binary tree as a subgraph. And another way to think about this theorem is that for every forest f, every graph of sufficiently large pathwidth contains f as a minor. And these 2 segments are equivalent. And actually here you get the best possible bound. So if you want to get a forest f as a minor, all you need is to make sure that your graph has pathwidth at least the number of vertices of f minus 1. And that's as small of a bound as you get here, because the complete graph on the number of vertices of f minus 1 vertices has pathwidth number of vertices of f minus 2, and it doesn't contain f as a minor. And the proof of this has also become shorter and simplified a few times, most recently by Seymour. And this proof is really less than a page long. So it's really elegant. Just go see that proof if you haven't already. Now, okay, something is wrong. I'm not moving back.
Wrong direction. So there's another button.
Okay.
Yes.
All right. That was a lot of spoiler. So. Okay. So, if you want to understand large pathwidth in terms of minors, then forests are all you need to think about. And if you want to understand large pathwidth in terms of subgraphs, then subdivided binary trees are all you need to think about. So it's time to ask, what about induced subgraphs? And this is an entirely different story from the get-go. For instance, the four constructions we saw before, they're all now central. Meaning, so you have these 4 constructions of graphs with arbitrarily large pathwidth. And if you just focus on one of the constructions, let's say this one, then there is no way you can find induced subgraphs of large pathwidth that belong to any of the other 3 constructions. In other words, if you want to prove a theorem that says, look, here's a list of graphs, and every graph of sufficiently large pathwidth contains an induced subgraph of large pathwidth from this list, then these 4 constructions must be on your list, or else it would be false. And there's nothing else that comes to mind immediately, so let's just conjecture that this is true. Every graph of sufficiently large pathwidth contains an induced subgraph of large pathwidth that is either complete or complete bipartite, or a subdivided binary tree, or the line graph of one. And this is like as elegant of a theorem as you get to prove here. And this is false, as you saw a few seconds ago. And there are actually 2 counterexamples. So one by this very large group of authors, and the second one is, this has actually been around for over 10 years. So Pahoda came up with this when he was an undergrad in Princeton, working with Paul Seymour. And also James Davis came up with it, like rediscovered it independently a few years after, in a different context. And now I'm going to tell you about these 2 constructions in details. So the first one, we ended up calling them interrupted constellations, which is a bit of a mouthful, but there are actually really solid reasons behind the behind the naming. So there's this whole machinery of constellations we developed with Maria and Sophie, which is a pretty useful tool we use quite often. But I'm not going to tell you about the details of that. I don't get to tell you about the details of that. But anyways, so in interrupted constellations, we have this parameter S. And so an interrupted S constellation is a graph that consists of a stable set of S vertices. And I'm going to consider them to be linearly ordered. And there's also a path outside this stable set. And by the way, from now on, whenever I use the word path, I mean an induced path. And here is how the adjacency works in this graph. Every vertex in this stable set has at least one neighbor in the path. But every vertex in the path has at most one neighbor in the stable set. So vertices in this stable set do not have common neighbors on the path. And so whenever you have 3 vertices in this stable set, and if you think about any path between the bottom 2, then the top one, the third one, must have a neighbor in that path. In other words, if you remove a vertex from the stable set and all its neighbors, then all the vertices in the stable set below the vertex you just removed, they all fall into different components. And here's a picture of an interrupted 4 constellation, which I assume is not quite helpful, so let's see, where is it coming from? Okay, so here's how you build an interrupted 4 constellation. You start with a path and 4 vertices in the stable set. The first 2 vertices can do whatever they want. And from the third vertex on, whenever there is a gap between neighbors of 2 distinct people below, then the third vertex must have a neighbor in it, at least one neighbor. And that is the only requirement. The third vertex can do whatever else it wants. So here are the gaps between neighbors of x1 and x2. And I insist, we do not need to care about the gaps between neighbors of the same guy. So x3 is going to have at least one neighbor in these gaps and can do whatever else it wants. And now we have the gaps between the neighbors of x1, x2, and x3, and x4 is going to have at least one neighbor in each one of them. So you get the idea.
So, the top vertex always with this neighborhood is a star cut set of the whole graph, basically. So if I remove the top vertex and its neighborhood, all the lower vertices lie in different components?
Yes, that is true, and more than that is true. All these different vertices, as you said, they fall into pairwise distinct components. Yes. It's not just a cut set, it separates all of them pairwise.
Mm-hmm. So when you say this gap, you look, so for the x4, you want to look for gaps involving x3 and other vertices, right?
I'm thinking about the gaps between 2 consecutive neighbors of any 2 distinct vertices below.
Oh, any 2. I see.
Although it actually suffices to look at x3 and the others because of the property.
Yes, because they've already been separated before by x2. I mean, you don't have a gap between 2 neighbors of x1 and x2 that has already not been interrupted by a neighbor of x3, because that's what x3 did in the previous step.
I see. Okay.
But anyways, the main idea is that, as you guys mentioned, when you remove that guy and its neighbors, then all the vertices in the stable set below fall into pairwise distinct components. Okay, now, okay, and this gives you a new construction of graphs with large pathwidth. So first of all, if you have an interrupted constellation with 2s plus 1 vertices in this table set, then it has KSS as a minor. It actually has it as an induced minor. You don't need to remove edges. Which means the pathwidth is at least s. Actually, the pathwidth is at least 2s when you have 2s plus 1 vertices, but I'm trying to make a point about the KSS induced minor here, which is something I'm going to come back to later. So they have arbitrarily large pathwidth, and it's easy to see that they're K4 free and K3 free. And what is more interesting is that they do not contain induced subgraphs isomorphic to any subdivision of a radius 7 binary tree or the line graph of 1. Why? Because, so suppose it does, I have an induced subgraph, for instance, which is isomorphic to some subdivided radius 7 binary tree. So let's forget about the root of the binary tree. This means you have two induced subgraphs in your graph that are connected. They're isomorphic to subdivisions of a radius 6 binary tree. So you have two connected induced subgraphs. Let's call them x1 and x2. And they both have pathwidth bigger than 2 because they're subdivisions of binary tree of radius 6. And they're anti-complete. Anti-complete means disjoint and with no edges between them. But how are you going to contain something like this? So here's the path, L, and you have this stable set of vertices. So this is an induced subgraph of pathwidth more than 2, which means it contains at least 2 vertices from the stable set. If it contains 1 vertex from the stable set, the rest of it is just contained in a path. And that is a graph of pathwidth 2. And the same is true here. So now let's think about the topmost vertex in the stable set that belongs to either one of these. Let's say it's called x1 and it belongs to the induced subgraph x1. And now let's choose 2 vertices in x2 that belong to the stable set, and they're as close to each other as possible. So let's call them x2 and x2 prime, and they both belong to the induced subgraph x2. And so because this is connected, there is an induced path between these, and because these two were chosen to be as close to each other as possible, this means the rest of the path is completely contained in L. If it's going to go back up somewhere else in the stable set, I'm going to just choose that path. That's shorter. But now this is a gap between the neighbors of these two guys, and this vertex is on top, so this must have a neighbor. But we said these two are incomplete. And the same idea works for the line graph. So the whole point is that you do not contain two anti-complete connected induced subgraphs of large pathwidth or tree width. Okay, so this was the first counterexample, and this is really a new construction. So you need to think about this as independent of the other 4 constructions we see: complete graphs, complete bipartite graphs, subdivided binary trees, and their line graphs. So the other counterexample, the other construction, we called them arrays. Again, because the original authors did not give them any names, so we needed to call them something. Again, there is this parameter t. So a t array is a graph that, once again, it consists of a stable set of t vertices, and it's linearly ordered. And this time, instead of 1 path, I have t paths. So t is also the number of paths that are pairwise disjoint and anti-complete, and they're also disjoint from the stable set. So every vertex in the stable set has a neighbor in each path. Every vertex in each path has at most 1 neighbor in this stable set, so you don't have common neighbors. And whenever you traverse each path from one end to another, you see the neighbors of the vertices in the stable set in the exact same order. So here is, for instance, a 3 array, and when I traverse L1 from this end to that end, I first see the neighbors of x1, and then the neighbors of x2, and then the neighbors of x3. And the same is true for all 3 of the paths. And this gives you a new construction as well. Again, a T array contains KTT as an induced minor. This is obvious from the definition. You have T vertices in this stable set and T pairwise anti-complete paths. So the path width is at least T. And again, it's easy to see that you don't contain K4 and KT3 as an induced subgraph. And again, you do not contain induced subgraphs that are isomorphic to subdivisions of large binary trees or their line graphs. And this time you need to deal with larger radius. 64 works, and I'm not sure if it's optimal. And the proof is a little finicky. I'm not going to show you all the details of it, but somehow the idea is to, so here is, for instance, your huge array.
So when you say T64, do you mean the radiuses?
A subdivision of the radius 64 binary tree.
Okay.
So if you have, so here is your huge array. So somehow the neighbors are lined up along these paths. So suppose it contains an induced subgraph, which is a subdivision of a massive binary tree. Now, what I'm going to do is I'm going to contract the stars centered at these vertices just all into one vertex. Just think about all the edges that are incident with this guy and contract them all into this vertex. And do it for every vertex in the stables. So what you get is a graph that looks like this. So these are the vertices in the stable set, and you get these huge linkages between them. And because these guys might have like a lot of neighbors on each path, you also have some cycles, and I don't know, probably some paths sticking out of each vertex, right? And this whole thing, no matter how many vertices you have here, and no matter how big these linkages are and how many cycles you have, this whole thing has bounded pathwidth. I mean, this has like pathwidth at most, I don't know, 200. I mean, if you want to bug your students, just ask them to prove that this has pathwidth at most 200. But it's true. But how did they get to this graph from that? I had a bunch of stars, of which the centers are at distance at least 3. Which means if I have a subdivision of a huge binary tree here as an induced subgraph, I can remove some of the branches and assume that I have a very long subdivision of a huge binary tree as an induced subgraph. So these paths are actually really long. Which means if I'm just contracting stars of which the centers are pairwise far apart, I'm never going to merge 2 degree 3 vertices into one another because this path is huge. Which means after the contraction, I'm still going to contain a large binary tree subdivided as a subgraph or induced subgraph. But this thing has a small pathwidth. It's not going to contain a large binary tree as a subgraph.
When you define the array, you don't allow subdividing edges on this.
No.
No, I see. So, it's,
Not at all.
so that's why it's
Yeah.
small
Yes.
radius.
Okay, so somehow this is the idea. I mean, to make it precise, there's a fair bit of technical work you have to do. Okay. So this is a new construction. It is independent of complete graphs, complete bipartite graphs, subdivided binary trees, and their line graphs. And what is more important is that it is also independent of interrupted constellations. So you can prove that interrupted constellations do not contain induced subgraphs isomorphic to a 7 array, and arrays do not contain induced subgraphs isomorphic to interrupted 8 constellations. And I'm not going to share the details of this, but somehow the same ideas work. Okay, so you remember we had this conjecture that every graph of sufficiently large pathwidth has an induced subgraph of large pathwidth that is either complete bipartite, a subdivided binary tree, or the line graph of one. And this turned out to be false because of interrupted constellations and the arrays. So let's just add them to the list and make another conjecture. Could it be true that every graph of sufficiently large pathwidth contains an induced subgraph of large pathwidth that is either complete bipartite, a subdivided binary tree, or the line graph of one, or an interrupted constellation, or an array? I mean, this would still not be a disaster. You're doing induced subgraphs, you wouldn't expect anything that neat. But this one is also false. That's not terribly false. I mean, there is a counterexample, but the counterexample is not an entirely different story like these two used to be compared to the first 4 outcomes. So let me first tell you what the counterexample is, and then we'll discuss. Any questions so far? Okay, good. So there is this construction of graphs I'm going to tell you the definition of, and in order to do that I need to tell you about strings of numbers. So I'm going to define this sequence of strings of numbers, which I'm going to call the zigzag strings. So you have this sequence of strings of numbers. zt for every positive integer t is a string of numbers from 1 up to t. And the definition is recursive. So z1 is just 1, z2 is 1 and 2. And when you're defining zt, what you do is you start with 1, and then you're going to ascend like zt minus 1. You're going to descend back like the inverse of zt minus 2, and then you're going to ascend like zt minus 1 again. And if you write this down, you'll get z3, z4, z5, z6, and so on and so forth like this. So this may not be quite illustrative, so let me show you a picture. So these are z1 and z2. z1 is just 1, z2 is just 1 and 2. So I'm going to construct z3. What I will do is I start with 1, and I'm going to go up like z2. So z2 just goes up, and I'm going to do that. And then I'm going to come back down like the inverse of z1, but z1 doesn't move at all. So I'm not going to do anything. And then I'm going to go back up like z2 again. So let's construct z4. Start with 1. I'm going to go up like z3, and z3 goes up, up. And I'm going to do that. And then I'm going to come back down like the inverse of z2. z2 goes up. I'm going to come back down. And then I'm going to go up like z3 once again. Right? So let's see another example. z5. I'm going to go up like z4. I'm going to come back down like the inverse of z3. So z3 goes up, up. I'm going to come back down, down. And then I'm going to go up like z4 once again.
So I'm sorry, but does Z3 have 4 elements or 3 elements?
It's got 3. It's a string with 3 characters. 1, 2, 3.
1, 2, 3. Not
Yes.
1, 2, 2, 3.
No, it's 1, 2, 3.
So you never repeat the same number.
No.
And so you can imagine what a monster z6 is going to be. And then I'm going to construct a graph. For each t, I'm going to construct a graph z, like gzt, which I'm going to call the zigzag graph. And so what is the zigzag graph with parameter t? You start with a stable set of t vertices, again linear the order, and you have t pairwise disjoint and anti-complete paths. And for each path, you're just going to walk through the path and you pick up neighbors of the vertices in the stable set according to the string zt. So if you remember, z6 looks like this, what you see on far right in this picture. And then if you just rotate this by 90 degrees, this is what you see for one path, and you actually have 6 of these paths. But what you see between each path and the stable set is exactly the same like this.
This is 6 paths. So for each of
Because you're looking
Yes.
at D6.
I have
I see.
6 paths, and this is just one of them. But for each one of them, you see exactly the same thing. Right?
Oh, so it's same copy, so you don't use G1, G2.
Yeah. Because, I mean, the whole point is that I want to keep the big, complete bipartite induced minor to make sure this is a graph of large pattern. Turns out I actually don't need to, but let's not.
It's basically a mixture of an array and what was the Death Star called?
It definitely wasn't called the Death Star. It was called an interrupted constellation.
Yeah, right.
Yeah.
Because I have this path and the independent set that. But now I have that each time I want to go from like something that sees x3 to something that sees x5, I have to walk through a vertex that sees x4.
Yeah, something like that is almost true. You're making a fair point, but let's make it precise.
Yeah.
So, yeah, okay. So, what we have to take into account here that this, okay, first of all, this is a new construction once again, meaning this gives you graphs of arbitrarily large pathwidth, and you can prove that it doesn't contain induced subgraphs of large pathwidth that are complete bipartite, subdivided binary trees, or their line graphs. And actually, the way you prove this is really similar to the way you prove the same thing for the arrays, like we saw here. So I'm gonna wait for 10 seconds. Okay. So actually, the way you see this is similar to the way you see the same thing for the arrays. And what is important here is that they're also independent of the interrupted constellations, which is again similar to the way you prove it for the arrays. So all of these things are really quite similar. The problem is that these are also really different from the arrays. So these things, no matter how large T is, they never contain 4 arrays as induced subgraphs. So this is really a new 7th construction. But okay, I'm not going to show you the details of these proofs, but what I'm going to tell you about is this characteristic property that the zigzag graphs and the arrays share, and this is what really distinguishes them from the interrupted constellations. So you remember a few minutes ago when I was talking about the interrupted constellations, I said whenever there is a path between 2 vertices in the stable set, then any vertex in the stable set that comes after them in the linear order must have neighbors in it. And if you think about it for a moment, in the arrays, something similar happens. Whenever you have a path between 2 vertices in the stable set, then whatever comes between the 2 vertices in this stable set must have neighbors in it, right? And somehow, miraculously, the same thing happens here. Whenever you pick a path between 2 vertices in the stable set here, like I don't know, if there is a path between x2 and x5, then you're always going to contain neighbors of x3 and x4. So from this point of view, they're really the same as the arrays. They're not induced subgraph the same because they do not contain 4 arrays as induced subgraphs. But from the point of view of who sees who without being interrupted by neighbors of who, they're really the same as the arrays. And this somehow turns out to be the important property that distinguishes them from the interrupted constellations. And this is what I'm going to call as a distorted array. I'm going to define as a distorted array. So this time we have 2 parameters, Q and T, and a Q distorted T array is a graph that consists of T vertices in a stable set, T pairwise disjoint and T-complete paths. Every vertex in the stable set sees each path. Every vertex in each path has at most 1 neighbor in the stable set. And whenever you pick 2 vertices in the stable set, and you pick a path between them, then everybody in between, except possibly for a few, and that a few has to do with the parameter Q that you choose, everybody must have neighbors. And Q is fixed. So you fix Q, and then you choose T to be whatever you want. And it turns out even if you do this, you still get constructions of graphs for each choice of Q. When you allow T to be as large as it wants, you get graphs of arbitrarily large pathwidth that are really independent of complete graphs, complete bipartite graphs, subdivided binary trees and their line graphs, and interrupted constellations. So even if you allow for only a few vertices in between to miss the path, you're still in good shape. And if you think about it for a moment, arrays and the zigzag graphs, they're both examples of one distorted arrays, right? Everybody in between must have neighbors. I have this strict equality here.
Oh, I see. So you don't have equality. Okay, I was thinking.
That's
So distorted.
I mean, strict inequality, yes. Okay. So once again, for each choice of Q, if you just allow T to be as large as it wants, you get a new construction. And okay, it's been a long day, and it's time to take another look at the list of graphs of large pathwidth we have. And I'm going to replace arrays by distorted arrays, like the most general thing that makes sure we're not going to run into any counterexample that looks like the zigzag graph. And so we can make another conjecture that every graph of sufficiently large pathwidth contains an induced subgraph that is coming from one of these 6 constructions. And in a moment, you're going to wish you made that conjecture because that is true. So this, ladies and gentlemen, this is the pathwidth theorem for induced subgraph. If you have a graph of sufficiently large pathwidth, then it contains an induced subgraph of large pathwidth that is either complete bipartite, subdivided binary tree, line graph of 1, an interrupted constellation, or a distorted array. If you want to be a little more careful about how the parameters work here, then you could call this first group of outcomes, this first 4 outcomes, the basic abstractions to bounded pathwidth. Then this theorem is telling you that every graph of sufficiently large pathwidth, in every graph of sufficiently large pathwidth, if the reason why pathwidth is large is non-basic, then you contain either an interrupted constellation with as many vertices in the stable set as you want, or an array, a T array, for T as large as you want, but your array is a little distorted. And the distortion is this neat function of the size of the basic abstraction you exclude at the beginning. So what you have to take into account here is that the distortion does not play any role whatsoever in the magnitude of the pathwidth here. I mean, you should think of T to be massively larger than R or any function of R. So
what is the bound of the pathwidth for distorted arrays?
doesn't have to do with this parameter. It is at least T.
At least 2. Okay.
Why? Because you have KTT induced line. You have T vertices in the stable set, T pairwise is trying to complete path, and each path sees each vertex. Okay. Alright, so this is the point I wanted to make to show you the summing of the theorem and to convince you, hopefully, that this is an efficient list of unavoidable induced subgraphs with large path. Ask questions.
How does W relate to R and S?
I don't think anybody on this planet knows that. This is a, it's just
Just some function.
I mean, just massive sequences of nested Ramsey things. I mean, it's just.
Yeah, but do you have like some conjecture or some lower bound?
I don't think anything like that is even conceivable.
Oh, what does a large mesh contain?
What is a large what?
Large mesh contain?
Okay, this is
I got large wall.
Mesh? Oh, wall. Yes, big walls contain subdivisions of big binary trees, as in the subgraphs, and their line graphs contain line graphs of binary trees.
So you have to introduce these distorted arrays. You can't just say, I take the zigzag graphs and your K arrays or T arrays and then this works. You have to do these distorted guys?
So are you asking, is there a third construction? Like something?
Yes, I'm basically asking, was this necessary? Or like, did you have to go to something more general than the explicit construction that you have?
So what I can tell you is that the way we came up with the zigzag graphs, you see it's a random construction. I mean, the zigzag sequence, I see it's cute and beautiful, but there's nothing really robust about it. It's just, so we never tried to find different sequences of not like strings of numbers so that when you put them on the paths as the neighborhood of the version of the stable set, you get the same property. But the point being, I think the point of the third outcome, the main point about it is that it shows you that you can't just hope to get the Proto-Davis graphs as another outcome, because, and this is really different from the case of interrupted constellations, because interrupted constellations are virtually the same as what originally was defined by the long list of authors, and we do get them exactly them as induced subgraphs. So the hope would be to just get the arrays themselves as induced subgraphs as well, but the zigzag graphs show you that this is not going to happen.
But zigzag graphs are like one distorted array.
Yes.
So do you know that you need to take something bigger than one distorted arrays?
That's an excellent question. I was hoping if somebody's going to ask it. That's open.
Okay.
It might be true that you just need one distorted arrays in this theorem. We don't think that's true, but we also didn't try that hard to find a counterexample. I mean, but it would be nice to know if that's true. Could it be true that you can always get the property that whenever you pick two vertices in a stable set and a path between them, then everyone in between must have neighbors? It might be true, but still, even if that is not true, this theorem is efficient because even if you allow for a few people in between to not have neighbors, you still get a construction that is different from the other 5 constructions. So it doesn't interfere with that. Questions? Good. So I have like 15 more minutes, right? I wanted to tell you a little bit about the proof of this, and you can tell if the segment of a theorem takes you 45 minutes to talk about, then the proof is going to be. But let me just tell you how the general idea of the proof works. So you see, the proof of this is in 2 major steps. I mean, there are 100 different steps, but there are 2 main steps in the proof. So you remember a few minutes ago I told you about the interrupted constellations containing arbitrarily large complete bipartite induced minors. So when you have 2s+1 vertices in the stable set, then you contain kss as an inducement. And the arrays do contain large induced minors because it's obvious from the definition. And complete bipartite graphs themselves are just complete bipartite induced minor models. So this theorem implies that every graph of sufficiently large pathwidth contains either a large clique or a subdivision of a large binary tree or the line graph of one as an induced subgraph, or it contains a big complete bipartite induced minor. This implies that. And what is true is that that theorem also implies this. And that's the first step in the proof of this theorem. So you first prove that instead of complete bipartite graphs and interrupted constellations and distorted arrays, you can get a big complete bipartite induced minor model. And then you prove a second theorem, that in any graph, if you contain a sufficiently large complete bipartite induced minor, then you contain as an induced subgraph either a big complete bipartite graph or an interrupted constellation with as many vertices in the stable set as you want, or a distorted T array with T as big as you want, and distortion is small. Or you get a subdivided wall or the line graph of a subdivided wall, but that is good because those things contain subdivided binary trees and their line graphs.
So that part you don't have to assume the pathwidth is round?
No. That's just a statement that tells you what exactly are the unavoidable induced subgraphs with a massive complete bipartite inducement. And so the second step, the second theorem, is just an entirely different story. And from now on, I'll try to tell you a little bit about the proof of the first step. So the first step tells you that if you have a graph of sufficiently large pathwidth, then it contains either a big clique or a big complete bipartite induced minor, or it contains some subdivision of a large binary tree or the line graph of it as an induced subgraph. And containing a subdivided binary tree or the line graph as an induced subgraph is qualitatively the same as containing a big tree as an induced minor. This is something you can easily check. So the first major step in the proof is this theorem, that for every tree T, if you have a graph of sufficiently large pathwidth, then it contains either a big clique or a big complete bipartite induced minor, or it contains your tree T as an induced minor. Right? So okay, I'm going to try to show you a little bit about the proof of this. So the main idea is this notion of a seedling. So what is a seedling? You have 2 non-adjacent vertices. Let's call them x and y. and there's this huge linkage between them, so a set of pairwise internally disjoint paths. And the linkage is not necessarily induced, meaning there might be chords between paths. But the property is that it's not only it's not induced, it really resists being induced. So you never contain in this whole induced subgraph, you never contain an induced linkage that is relatively large between x and y. So huge here is a huge function of large. And does that make sense? So acetylene is a massive linkage between two vertices that not only it's not induced, it doesn't contain an induced linkage between the same two vertices that is relatively large. And the important point here is that I'm not saying the linkage does not contain a sublinkage. I'm not saying you think about some of the paths in the linkage. I'm saying no matter how you reroute things in here, you're never going to get an induced linkage. I mean, it's important to understand this definition. This is really the main idea in the proof. And why am I calling this acetylene? Because this is exactly where I'm going to get my tree as an induced minor. So, okay, what do we want to prove? We want to prove that every graph of sufficiently large pathwidth with no big clique and no big complete bipartite induced minor, it contains an induced minor isomorphic to my favorite tree. So the first step is to show that the graph, we can actually assume that the graph has large pathwidth, large tree width. And I'm not going to show you the details of it, but basically the idea is that, okay, if you have a graph of huge pathwidth, you contain, by Robertson and Seymour, you contain your favorite tree as a minor. So you think about the minor model. And so the point is that there might be edges between these branching sets, right? I don't know it because this is just a minor model. But I can Ramsey this. So I'm not sure if you've seen this, but there's this standard Ramsey theoretic technique. I think Kiersten and Penprice were the first who used it. That this is basically the product version of Ramsey's theorem. That if you give me a tree T, I can give you another tree, let's call it H, that is huge, such that any graph that contains H as a subgraph, it either contains your tree T as an induced subgraph, or it contains a big clique, or it contains a big complete bipartite graph. And if you just apply it here, if you get your tree as an induced subgraph in the contracted graph, then you're getting the induced minor. And if not, you're getting a lot of these branching sets that are pairwise not anti-complete, or in a complete bipartite sense. I think you get the idea. You get an induced subgraph that contains a big clique minor, so it has large tree. So the whole idea here is that because I'm assuming that the tree induced minor is not there, I can pass from large pathwidth to large tree width. So that's the first step. The second step is to use large tree width to get a large acetylene. And this one I'm not quite sure if I'm going to have time to show you the details of it, but the general idea is it's coming from this theorem we proved, so by we I mean Maria, Sophie, and myself, with Tara, Abrishami, and Bogdan Alaku. We proved this some 2 years ago. That if you have a graph of large tree width, and it doesn't contain a basic obstruction to large tree width, by that I mean big clique, big complete bipartite graph, subdivided wall, or line graph of a subdivided wall, then you can find a big set of vertices such that between every two of them, you have a lot of pairwise internally disjoint paths. So this is something like, it's like a subgraph of your graph that is a subdivision of the complete graph, but except for one path between, instead of one path between two vertices, between each two vertices, you have a lot of. So it's like a complete multi-graph that is now subdivided. And you can take this as a subgraph. And then what you do here, this is technical, but you essentially just Ramsey the devil out of this thing. You just do all sorts of Ramseying arguments to convince the huge linkage between these two to be acyclic, meaning it's not going to contain an induced sublinkage, or you can make the whole thing to be induced, but now you contain an induced subgraph, which is a subdivision of a complete graph, which means now you have a subdivision of anything you want as an induced subgraph, in particular your tree. And that's just an induced plane. And is it coming back?
Yeah.
Yes. So, and the third step is to use the linkage, and I have like 5 more minutes, so we'll see where this is going to go. But so here's my huge linkage from X to Y, and this is a seedling, meaning this is a big linkage, but in this whole induced subgraph I can't find an induced linkage between X and Y that is relatively large. And now what I'm going to do is, so for each one of these paths, okay, first of all, by Ramsey I can assume that these paths, these interiors, are pairwise not anti-complete. I mean, if I get many of them that are pairwise anti-complete, that's an induced linkage. So for each path, I'm going to traverse it from this end to that end until the first time this whole red subpath I'm covering sees a lot of other paths. And a lot here is a huge number, let's say 100. Which means this bit is seeing at most 99 paths. This sees at least 100. So this one may see 1, may see 1,000,000. But this is the first time I'm jumping from 99 to 100. It might be a massive jump. And I'm going to do this for each one of these paths. Now, okay, let's see. So this red bit here sees 100 other paths, at least 100. But let's just fix a set of 100 of them. And let's associate that set of 100 paths to this red bit. And I'm going to do this for each one of these red bits. So for each one of them, I have a set of 100 paths, other paths, that there is an edge between this red bit and each one of them. And now I'm going to put a digraph on this set of interiors. So these paths are, I don't know, P1, P2, P3, P4. And so for each one of these PIs, I'm going to make this adjacent to those 100 paths that I've chosen from the set of all paths that this red bit sees. The point is, this may see a lot of other paths. I'm just fixing a set of 100 of them. And this set of 100 paths for P1 might intersect the set of 100 paths for P2. It might actually be the same set, doesn't matter.
Whatever bidirected edges, right?
Yes, and the digraph here is not simple. You might have arcs in either direction between the same pair of vertices. Now, okay, I have this huge digraph. By huge, I mean huge number of vertices. And in this digraph, every vertex has out degree 100, exactly 100, right? Which means if I just think about the underlying undirected graph, then it doesn't contain a big clique, because if it contains a big clique, then by Ramsey it contains a big transitive subtournament when I put back the orientations of the edges. And now when you have the transitive subtournament, the source of the tournament has everybody else as an outneighbor, but every vertex has a small outneighbor, a small number of outneighbors, right? So the underlying undirected graph doesn't contain a big clique, so it contains a big stable set. Ramsey. So what does this mean? It means if I just think about these red bits, and now they're a stable set in the digraph, it means that set of 100 paths for each one of them is just outside their own set, because between them I don't have arrows. Does that make sense? So the set of 100 paths for P1, it's just outside, and I'm not going to add the edges between X and this and Y and that end, but secretly these are just paths of the seedling. So these are those paths that P1 sees, those that P2 sees, P3, and so on and so forth. And these might still be the same set of paths. They may have a lot of intersection, but I can somehow disentangle them, right? I mean, if I need 100 instead of 100 paths just privately for this guy, I'm going to start with 400 paths for each one of them, and I'm going to keep 100 for this, and then 100 for that, and then 100 for that, and then 100 for that. I just need a private set of 100 paths for each one of them that they see. I'm not saying P1 doesn't see any of the paths from the other set. I'm just saying I need 100 paths privately for this guy, distinct from the other set of 100 paths for that guy. Does that make sense? If you need 4 disjoint sets of 100 paths, just start with 4 sets of 400 paths, and pick 100 for this one, remove it from the other 3, pick 100 for that one, remove it from the other 2, pick 100 for that one, remove it from the last one. Does it make sense? Okay, and now, here's the fun part of the proof. If you think about it for a moment, you can just traverse each one of these paths back until the first time you see a neighbor of P1. And if you just pretend P1 is a vertex, you just contract it into a vertex, you get a ceiling between P1 and what? And now, let's just think about P1, P2, P3, and P4. We said this is the first time this thing is going to see 100 other paths, and this sees only 99, and this sees only 99 other paths. And the same is true for each one of them, which means if I do another digraph and saying, this time I'm saying, who sees who, honestly? If P1, the red bit, sees any other path, just put an arrow between them. This time, actually, honestly, the digraph has bounded out degree at most 99 for each vertex. Which means, again, I can get a big stable set of them, which means a lot of these things are going to be pairwise anti-complete. And this is how you get the induced minor model of your tree. So you have this vertex X, and you have P1, P2, P3, P4. And these are pairwise anti-complete. And these are going to be branching sets associated with the children of X. And now, out of each one of them, by induction on the radius of the tree I want to get, I'm going to grow the rest of the tree. And because these are pairwise anti-complete, the main concern about is this going to be an induced minor is now rectified. There is still a bit of a concern, what if there are chords between, the sets further into this branch and that branch? But those are easy, you can just Ramsey them, and because you do not contain a bit complete bipartite induced minor, you can get rid of it. But this main step to get the vertices in the same level of the tree, branching sets associated with them to be pairwise anti-complete, that is the main tricky part of the proof. Okay, I'm going to stop here. Thank you.
Thank you. Questions? Do you have some open problems after some problems? Continuing this direction?
I think the open problem, like the problem that somebody, I don't know who mentioned this, but it would really be nice to see if we can really get one distorted arrays instead of arrays with bounded distortion, where the bound is a function of the size of the basic abstraction. I mean, that is open. I don't think it makes much difference in the content of the theorem, but it would really be nice to see if there is a counterexample.
At the first step here, how did you find the vertex that sees 100 paths? Is it by Ramsey?
Yes, the first step is to say, here's your linkage, because it is a seedling. By Ramsey, you can assume that you can keep a lot of these paths, and they'll pairwise see each other. Because the other outcome is you can keep a lot of these paths, and they're pairwise anti-complete, but that is already an induced linkage, right? So this whole path sees everyone else. So I'm going to start from here and walk through it until the first time I see, okay, maybe not everyone else, but at least 100 other paths.
So that 100 is from Ramsey. You can.
Yes.
Okay.
Yeah, I mean, the way the constants here depend on one another, it's really complicated, but I hope you see it.
If I'm interested in the path version of tree independence number,
Yes.
then all of your obstructions except for the click remain obstructions, right? Do I get something for this path independence number from your theorem?
So I think you're basically asking, is the strengthening of the main theorem here true, that
Yeah.
you just forget about the click outcome, and is it true that if I exclude those things, then
Or-
true independence number is bounded?
That's it.
Path independence.
Path independence number is not. There is no counter. I don't know a counterexample of that. It might be true, but it would also be really hard. I mean,
Yeah,
as you would
probably.
expect, like very very special cases of that are open. Like, is it true that if I exclude, I don't know, a long path, and a big complete bipartite graph as an induced subgraph, which is a very special case of this thing, does that bound the tree independence number? Even that is open.
But you don't know any additional constructions.
No. That might be true.
Yeah.
It might be true.
So does this allow you to say, like, if I've got a finite list of graphs, and I look at the graphs which have none of those as an induced subgraph, does this let you quickly say whether that will have bounded pathwidth or not?
Depends on what you mean by quickly. Like, can I do it quickly, or can a computer do it quickly?
The computer do it.
Yeah.
So algorithm for the
I mean, I'm not that quick in general, so not me, but I don't have an immediate. You see, I'm not even that quick in answering that question. So it's an interesting question. I don't know. We do have theorems. We again means Maria, Sophie, myself, and I think this one is also joined with Bogdan. Like that's an interesting point, because for instance, we have a theorem that tells you that if you exclude a finite set of graphs, so here is a hereditary class of graphs that is defined by a finite set of forbidden excluded and finite set of forbidden induced subgraphs. And now, just think about this class of graphs, and the question is, what should I have excluded to make sure that in this class, trivet is a function of the size of the biggest basic obstruction in the graph? So is it true that if I exclude just a big wall, line graph of a big wall, a big click, and a big complete bipartite graph, then trivet is bounded? And so, for instance, in order for that to be true, you need to make sure that finite set of graphs eliminates arrays, or otherwise your class contains graphs of arbitrary large pathwidth that do not contain a basic obstruction of large pathwidth.
Yeah.
And the converse of that is also true. So that's the main theorem. That if you have just a finite set of graphs, if it is true that excluding them implies there's not going to be a big array in your class, then you have killed all the reasons that are non-basic.
This was like all with fixed R.
Yes, yes. But that theorem is not constructed. It doesn't tell you what those finite graphs could be. It just says finitely many graphs. It just says you're excluding finitely many graphs, and it implies that as a result you're excluding sufficiently large arrays. That's it. And it's actually open. We mentioned this, I think, as an open question, that if I give you a finite set of graphs, then can you check in polynomial time that it has this property? I'm not sure if anyone knows the answer to that question.
Right, any other questions? If not, let's thank the speaker. All right, who wants to join the dinner?